So I am going to introduce now our next student, Miss Frid, will be sharing an amazing title. Well, it's not up on the board, but let me read it to you right now. Time Dilation, an investigation into the theory of relativity and its application in theoretical events. So get ready for an amazing cerebral presentation. Let's welcome Miss Frid. Forget to touch.
Would you believe me if I told you that there's a realistic theory of time travel? It has existed for over 100 years, and people have successfully executed it. Okay. Okay, I'm gonna stand up here. Okay. Good afternoon, everyone. My name is Twyla Frid, and today I'll be talking to you about time dilation. More specifically, an investigation into the theory of relativity and its application in theoretical events. I will try my best for the next 20 minutes of your lives to break down your ideas of time dilation and then rebuild your understanding so you're able to understand possible theories of time travel. Please don't run away now. I've worked hard on this presentation. This is a visual representation of two theories that make up the complete theory of relativity. But don't worry, we are not here yet. First, I'm going to talk about Newton's laws, and then the basics underlying principles of time dilation. More specifically, gravity, motion, and time. Newton's first law. Objects in motion tend to stay in motion, and objects at rest tend to stay at rest, unless acted upon by an unbalanced force. Newton's first law talks about inertia. If an object's at rest, it's not going to suddenly jump into motion, meaning it's not going to change, or if an object is moving, it's not going to suddenly change speed or direction. Newton's second law, force equals mass times acceleration. When an object's velocity increases, that is, it accelerates, there is a corresponding increase in the force that an object can exert. Say you throw a golf ball into the air. As the ball starts falling, it will start gaining momentum. You calculate the exact rate of the acceleration, and with knowledge of the mass, you can calculate the net force by multiplying mass and the acceleration. Newton's third law, every action has an equal and opposite reaction. Although many have heard of this law, only a few understand it. When working this law, you could consider a bike. When you start pedaling the bike, it creates an action that's pushing against the ground. Then the ground then creates a reaction, then pushing the bike forward. The reason the bike moves forward and the earth does not move backwards is due to the fact that the earth has a much greater mass than the bike. So the effect on the earth is much smaller, but it's still there. There is no such thing as being free from the force of gravity, for two reasons. Every object that has mass, so every object, exerts a gravitational force, even a pencil. And a gravitational force is never ending, no matter the mass of the origin object. So a pencil on an alien planet on the other side of the universe is affecting all of you, even if very slightly. Gravity is the force that keeps your feet glued to the ground, the orbit of the planets in its correct array, and many more things I will not discuss now, but some I will touch on later. The action or process of moving, or changing position or place, movement. This is a definition of motion, but it only touches on a brief summary of what motion actually is. There are other specifics you must know before hearing the rest of my presentation. For example, relative velocity. Relative velocity discusses the idea that moving objects only exist in relation to each other, and all objects are moving. But for this, we're going to pretend there's something called at rest. So as you can see here, car 1 is moving at 50 kilometers per hour relative to something at rest in this direction. Okay, so now we're going to add a second car. It is moving at 40 kilometers per hour in this direction relative to something at rest. So because they are moving in opposite direction, their speeds are added for the relative velocity, meaning that they are moving at 90 kilometers per hour relative to each other. They're moving apart from each other at 90 kilometers per hour. So now let's forget about car 1, and let's add a third car. It's down here, and it's moving at 100 kilometers per hour, relative to something at rest, in the same direction as car 2. Their relative speeds is 60 kilometers per hour, because they are moving in the same direction, so they are subtracted. Meaning that if car 2 was ahead to begin with, car 3 would be approaching it at 60 kilometers per hour. The speed of light is just under 300 million meters per second. But the speed of light contradicts Newton's idea of relative velocity, because it is a constant, meaning that nothing can go faster. It's a sort of universal speed limit. So no matter what the origin point is, it is never going to go faster than the speed of light. So I want you to think about this scenario. There's a train that is moving at half the speed of light. And there is then a headlight in the front of the train that is moving at the speed of light. So from this, you would assume that the light from the headlight would be moving forward at 1.5 the speed of light. This is in fact false though, because the speed of light is a constant, so it is moving at exactly the speed of light, even though the train that is being produced from is moving at half the speed of light. How we perceive time in everyday life does not encompass the full implications of time. It only touches on a small fraction of time. Linear time is the idea that time is ever flowing in one direction at a constant velocity, from one event to another, beginning to end. But in real and more complicated life, time has more variables. Time is not one-directional. The only thing that fluctuates in the passing of time is our perception of it. Past and future are the same, contrary to popular belief. Some physicists, for example, Carl Rovelli, believe that there's no real distinction between past and future in physics. We comprehend time in the way that we do. It's because to make us think that there's a sort of order to things. But that is only because that's our only way our brains can even come even close to understanding what's going on around us. Albert Einstein is one of the smartest people that has ever lived. He is responsible for most of the theories that we'll be talking about today, including this one. Time dilation is the fluctuation of time caused by gravity and velocity. In other words, the passage of time is not a constant. The faster you go, the slower time moves for you in relation to other reference frames. And the greater the gravitational force you experience, the slower time moves. Special relativity is a theory regarding objects that are moving at considerable fractions of the speed of light, that are not accelerating, what physicists call inertial reference frames. The premise of this theory is based off of two postulates. Postulate 1, that all laws of physics are the same for all objects that are not accelerating. And postulate 2, the speed of light is a constant in a vacuum. Other factors have to compensate for this constant. Time and length are these compensating variables. Time dilates and length contracts. In other words, special relativity discusses the idea of how time and length compensate for the constant velocity of light. I want all of you to imagine a train, a completely theoretical train that is moving at half the speed of light. Let's say your dear friend Bob over here is on that train that we just talked about. It is moving at half the speed of light, and there's a headlight that on the front of the train that is moving, that has light that's producing at the speed of light. As we talked about earlier, from this, you would assume that it is moving towards you on a platform at 1.5 the speed of light. But as I said earlier, this is false. The speed of light is a constant, no matter what. To understand this notion and how it applies to the headlight scenario with the train, let's examine this scenario. Your dear friend Bob, as I said earlier, is facing this mirror. He is shining a light at this mirror that is going straight there and straight back, but his position is perpendicular to the train's trajectory, meaning that the train is moving this way and he is facing this way. So, this is the perspective of an observer on the train. But let's remember here that the train is moving at half the speed of light. This is Europe's perspective from the platform. You see his light move diagonal to the mirror, because the mirror has moved since the light was produced. And now after the light hits the mirror, it is then going to move back on a diagonal back to Bob, because Bob has now moved past the point where the light hit the mirror. So there it is moving more than 5 meters. In fact, it is also moving more than 5 meters. Remember, this is because the train is moving half the speed of light. So to put this all together, we can see that from the perspective of somebody on the platform, Bob is experiencing more time because he is moving at half the speed of light. Just in case you guys didn't get this, I have another scenario for you. Okay, so this is a twin paradox. It discusses what would happen if two twins are separated. One twin stays on Earth over here, while the other twin goes on a little journey for about 30 years at half the speed of light. I apologize, I removed that in writing. Okay, so this is what this idea is based around. But I want to introduce one more little thing. Okay. They both have something called a light clock. A light clock is a box that has a light beam in it. It is moving straight up and then bounces straight back down again because there's a mirror on either side. Each time it hits the top or bottom, a second has passed. So both of the twins have this light clock. So let's look at this from twin one's perspective. When twin one looks at her own light clock, she sees it as going straight up and straight back down again. Sorry if you guys can't see that, but it's just going straight up, straight back down again. Similar to Bob and his mirror from the perspective of somebody on the train. But now let's throw a little twist in it. Twin two, when twin one looks at twin two's light clock, she sees it as moving on a diagonal, similar to how you perceived Bob and his mirror. Okay, so simple enough. When the twin 2 gets back, she will be younger, right? But it's a little more complicated than that. Because when we look at twin 2's perspective, when she looks at her own clock, it is moving straight up and straight back down again because she views herself as being stationary before the turn and as the Earth moving away from her at 50% of the speed of light. This is because of the first postulate. All laws of physics are the same for all inertial reference frames, meaning frames that are not accelerating. So there's no distinguishing between reference frames, which one is in motion and which one is stationary. So this means that when twin 2 looks at twin's 1 light clock, it is moving on a diagonal. So we're now in a state of disagreement. Both of the twins think each other is younger. The reason or solving to this theory lies in the turnaround. In the turn, twin 2 accelerates, meaning that special relativity no longer applies and general relativity comes into play, something I'll be talking about very soon. So when they get back, they both agree that twin 1 is 30 and twin 2 is 26. General relativity is the reason that 2 months and 1 day ago, physicists or scientists got the first photo of a black hole because general relativity explains the existence of black holes. As we know, special relativity applies in non-accelerating reference frames. But what happens when the frames are accelerating? Special relativity falls apart and general relativity comes into play. General relativity theorizes what will happen in accelerating reference frames and the connection between space and time. Time dilation in this theory is caused by the massive objects creating a gravitational force that is in turn warping time to move slower. The bigger the mass of the object, the bigger the dent in the space-time continuum, similar to a bowling ball on a trampoline. Black holes are a gravitational anomaly. They are formed by the collapsing of an object, normally a star, into an extremely dense singularity. Physicists do not know the exact nature of these singularities, but they theorize that it might have infinite density with no surface area or volume. Little fun fact, that's the wormhole from Interstellar. Up until about 2 months ago or a month ago, it was the most realistic or closest representation of a black hole. I already did that. To illustrate this, I want you to contemplate this scenario. There are two people. One person that is getting sucked into a black hole here, and an outside observer. So the outside observer watches the person's time that is going into the black hole start to move slower and slower and slower, and perceive to move slower, until it appears to stop. While the participant, she views herself as staying in the present, as everything around her accelerates into the future. But this is only a matter of perspective. Because time has slowed immediately around her, but beyond her immediate pocket, even a few centimeters away, time would be moving faster because there's less of a gravitational force acting on it. Black holes exert such an intense gravitational force that if matter passes the event horizon, it will experience physicists call spaghettification, the stretching of matter into a thin line. This happens because the gravitational force increases so intensely between such small distances that it will rip matter apart into something that resembles spaghetti. On April 10th, 2019, you may have heard in the news that the first photo of a black hole was taken. One of the key contributors in the programming side was a grad student at MIT. Her name is Katie Bauman. The first photo was taken using the Event Horizon telescope, but instead of being one telescope, it's actually 8 telescopes that work together to create one image. Because to take that image with one telescope, it would have had to be the size of the entire Earth. So the photo was taken of the black hole in the center of the M87 galaxy. And the photo proves once again that the theory of general relativity holds true. You can tell this by the light patterns around the black hole, and because they predicted that it would look exactly like that. One of the most common places that people encounter the theories of time travel for the first time are in movies. These are posters from 2 movies that have time travel in them. Endgame. Endgame talks about time travel through the quantum realm while discussing some possible paradoxes involved. But the physics in this is not quite accurate. By the way, I'm sorry if I spoiled Endgame for anybody, but it came out about a pretty long time ago, so I thought it was okay. Interstellar, on the other hand, is a much more realistic and scientifically based story. It does go into the realm of unrealistic, but not as frequently or as intensely. It talks about time travel through relativity and black holes. So it's much more scientifically based in evidence. Sergei Krikalev holds the record for the most amount of time in space, a total of 803 days, 39 minutes, and 9 hours and 39 minutes in space. Because of the rotation and movement of the International Space Station, he has traveled 0.02 seconds into the future. I told you somebody had time traveled. We know that time travel to the future is possible. Albert Einstein showed us 2 ways of doing that: moving at a significant portion of the speed of light, or being in an extreme gravitational force. When Sergei Krikalev was in space, he was moving at 27 580 kilometers per hour, which is much faster than the Earth's rotation, which is just 1,600 kilometers per hour. So he is moving much closer to the speed of light than Earth is. A wormhole is a shortcut. It is a rip through the space-time continuum, making it possible to travel great distances in a matter of seconds, and even maybe travel through time. I'm going to give you guys a little example of how most people in movies explain it. And it actually makes a little bit of sense. Okay, so if you can't hear anything, if you can't really see it, I'm sorry, but okay, so you want to go from point A over here, right, to point B over here. But this is going to take 3 million years, or some insanely long time, which is not able for, a human can't live that long. Okay, so why don't you just bend space-time and rip a hole through it? Such an extreme gravitational force can sometimes rip a hole through space-time. It has to be even stronger than what's in a black hole, though. Okay. There's a chance that wormholes can exist naturally, but our accessibility and ability to manipulate their location and traversability would be limited. For this reason, human-made wormholes come into play. There is no mathematical proof that time travel to the past is impossible. Despite this, many physicists believe that it is. There's been a couple theories regarding this. One of them is, so the steps to traveling to the past are: 1, create a wormhole. 2, separate the two halves of the wormhole. One goes on a little trip for about 12 years at close to the speed of light in this scenario. Then return it back to its origin place. Because of the movement of the side 2 in an inertial reference frame, it would have only experienced 8 years, while side 1, on the other hand, because it was not in motion, would have experienced 12 years. According to when someone enters the wormhole through side 1, they will exit 4 years into the past. There's more complications regarding time travel to the past. One of them is the grandfather paradox. This discusses what would happen if you went to the past to kill your grandfather as a kid. A normal family tree looks like this. Grandfather meets your grandmother, creating your father. Your father meets your mother, creating you. Okay, so simple. So now you go to the past to kill your grandfather. He's only lived to about 2. Meaning he never met your grandmother, meaning they never had your father, meaning that your father never met your mother, never creating you. Meaning now you can't go to the past to kill your grandfather. So he is now still alive, meaning that everything is back to normal. Great, right? But now you do go to the past to kill your grandfather. So he is now dead again. Simple things. 1, don't go to the past and kill your grandfather. 1, it's not too nice of a thing to do, and it just messes a lot of things up. And 2, if the physics hold true in this scenario, time travel to the past would be impossible because it would create a paradox. The theory of relativity is a simple theory, but it unlocks many secrets of the universe. For this reason, it can be regarded as an extremely complicated one, when in actuality it only discusses 2 ideas. 1, the closer you get to the speed of light, the more time dilates. The less time lapses relative to other reference frames, moving at slower speeds in inertial reference frames. The length of materials will contract to compensate for the static speed of light. And number 2, space and time are in fact one continuum called space-time, and the fabric is warped and curved by the mass or density of objects. This theory can help us expand humanity's possibilities and help us have a greater understanding of the universe around us. But it does not, on the other hand, answer all questions regarding time. There's still many that need answering. For example, some are, what is a world with no time? Is it possible to go faster than the speed of light? If so, what would happen to time? And is time a fundamental quality of reality, or instead a perception that our brains put on the world to understand or organize events and experiences? Maybe these questions that will be what my generation will answer. I would have a couple of thank yous to say. First off, I want to thank you, Jen, for always keeping me on task and putting up with my insane topic choice. Jason, for always helping me and giving me very insightful comments and emails that were extremely helpful. Reed, for always helping me and catching me when things were wrong, and also helping me when things were right. Mom, for putting up with me and also letting me try to figure out my weird passion of time travel and time. For my dad, for constantly helping me edit, lay out my ideas, practicing, and being very, very, very honest when something wasn't good enough. Thank you to Scott Massey for helping me choose my topic and giving me a really good basic understanding of what I was doing. And thank you for all of you for coming and surviving my presentation. That's a pretty good feat.
Welcome back. So, Miss Frid, it is my pleasure to formally declare that you have wholly and completely and in a magnificent way articulated such a complex topic. Congratulations, Miss Frid. You have met all the requirements of the Masterworks presentation.